to now, all the curve sketching you've done has been using transformations. Now we're going to develop a new technique for sketching curves using differentiation. To investigate this technique, we're going to use this cubic that you've done some work on before the program started. The program is divided into 3 parts. We begin by taking the cubic that you've already looked at and develop some ideas on curve sketching from that. Next we'll show you that these arguments apply to any general curve. And finally, we'll go on to apply these curve sketching techniques to a specific function that you haven't seen before. For the first part, here's the function f of x that we asked you to investigate before the program. You've already sketched this curve in block 2 using transformation techniques. We asked you to find out where the derived function is positive, 0 and negative, and this table summarises the results. When x is minus 2, the function value is 21, and there the derived function is 0. The derived function is 0 again here when x is equal to 1. And we'll go on to see just how the graph and the derived function are connected. Bob?
Well, part of the connection between the graph and the derived function we've already seen before, because we know that the horizontal tangents correspond to 0 values of the derivative. And for this particular graph, we've got a 0 derivative when x is minus 2, so a horizontal tangent, and a horizontal tangent when x is equal to 1. But what's more interesting is what happens to the graph where there aren't horizontal tangents. I think you can see that to the left of minus 2, the function is increasing. And what's the corresponding thing that happens to the derivative? If we look at the table underneath, we see that the derivative is positive. Now, in fact, the derivative is positive for another set of values, namely the values of x which are greater than 1. And if we compare that to the graph, we see that the function is increasing on that stretch too. And the last thing is that between minus 2 and 1, the derivative is negative and the graph is decreasing. Well, it would be nice to know if this correspondence is true for all graphs and not just for this cubic. Does a positive derivative always correspond to increasing and a negative derivative to decreasing?
What we've got to remember is that we're talking about increasing on an interval. And what the definition of increasing on an interval means is that all chords with endpoints in the interval have positive slope. So let's see how we would justify for this cubic that the positive tangents on the interval give positive chords, which means that the function is increasing on the interval. We know that the tangents have positive slope because the derivative is positive. What can we deduce about the chords? Well, let's look at this one. It has a parallel tangent attached to the curve somewhere between the endpoints of the interval. But we know that the tangent has positive slope, so the chord has positive slope. And that's what we wanted to know. Now that's true for any chord whose endpoints are in the interval, which justifies that the function is increasing on the interval. Now let's look at this part of the curve where the derivatives are negative. Why do the negative derivatives guarantee that the function is decreasing? Look at any chord with endpoints in the interval. The chord has a parallel tangent attached between the endpoints. The derivative tells us that the tangent has negative slope, so the chord has negative slope. And that's true for any chord with endpoints in the interval, which means that the function is decreasing. Now, the argument I've been using doesn't depend on the function being a cubic. It just depends on the sign of the derivative. For positive derivative, the function is increasing, and for negative derivative, the function is decreasing. So to summarise, we have that for nice, well-behaved functions, If the derivative is positive on the interval AB, then the function is increasing on AB. If the derivative is negative on an interval, then the function is decreasing on that interval.
Now I'd like to look at two important features of this graph. This peak and this trough. Well, how could we have predicted them just from this data? Well, let's look at what happens near -2. Just to the left of -2, the derivative is positive and the function is increasing. At -2 itself, the derivative is 0 and there's a horizontal tangent. Whereas just to the right of -2, the derivative is negative and the function is decreasing. So increasing, horizontal, decreasing identifies this peak. Now we're going to call a point like that a local maximum. Now the value here is larger than the values around about, so it is a maximum, but it's a maximum only locally because in fact there are larger values over here. So increasing, horizontal, decreasing identifies a local maximum. But you see, increasing is given by a positive derivative and decreasing by a negative derivative. So in terms of derivatives, positive, 0, negative gives a local maximum. Now, at 1, the curve goes from decreasing to a horizontal tangent to increasing, and that gives a local minimum. In terms of derivatives, it's negative, 0, and positive, which gives the local minimum. So for a local maximum, we need the derivative to be positive just to the left and negative just to the right. But for a local minimum, we need the derivative to be negative just to the left and positive just to the right.
So the derivative tells us quite a lot about what the curve looks like. If we investigate the derivative more, we can find out more about the curve. Right, let's look at the curve using this computer here and look at the tangents. Here's the first tangent, and the number underneath, 36, is the slope of the tangent. Here's another one with slope 18. And as we go along from the left, the tangents are above the curve. And they continue to be above the curve until we get round to this point here, where there's a tangent which crosses the curve. And now, as we increase x, the tangents are below the curve. Well, let's try to identify where the tangent crosses the curve. Here on the left, the slope is positive. It's still positive here, but it's smaller. It's decreased. It goes on decreasing, and here, at the local maximum, the slope is 0. The slope now goes negative and continues to decrease. But somewhere in this region, it must stop decreasing because it comes up to 0 again here. So there's a point where the slope stops decreasing and starts increasing, corresponding to the point where the tangent crosses over. This point is called a point of inflection. So we're looking for the point where the derivative changes from decreasing to increasing. And we can see that by looking at the graph of the derivative. We've got some values of the derivative, but let's plot the graph. Just to the left-hand side, the derivative is decreasing, and to the right, it's increasing. So, how are we going to identify this point of inflection?
Well, what was special about that point of inflection here? It was a point where the derivative of the original function changed from being decreasing to being increasing. Now, we've already seen once how we decide whether a function is increasing on an interval. All we have to do is to check its derivative and see that its derivative is positive. So, to decide whether the derivative is increasing, we'll have to take its derivative. That's to say, we'll have to find the second derivative of the original function. If I find that the second derivative is positive, it means that the derivative is increasing. And if I find that the second derivative is negative, then the derivative is decreasing. And that's exactly what we see here. The second derivative changes from negative through to positive. And that's a nice test for points of inflection. You don't actually need to plot the derivative. Now, for other curves, there are points of inflection where the second derivative changes from positive to negative. But the essential test is that the second derivative changes sign. So to summarize, for points of inflection, either you've got the second derivative is negative just to the left and positive just to the right, or it's positive to the left and negative just to the right. All right, well, let's try and sum up what we've done so far. Imagine that we're doing it for a curve for which we knew the equation but didn't know the graph. Well, what would we do? Well, first of all, we know what the function is. And then we could differentiate that function, and we would find the places where the derivative was positive, was negative, and was zero. And this would give us information about the horizontal tangents, about where the curve was increasing, and the intervals on which it was decreasing. It would also enable us to locate the maxima and minima, because the local maximum is given where the derivative goes from positive to negative, and a local minimum is where it goes from negative through to positive. All right, then we'd find the second derivative. We'd find out where it was zero, where it was negative, and where it was positive. And those changes in the value of the second derivative would locate for us the points of inflection. They're the points where the second derivative changes sign, either from negative to positive or from positive to negative. Well, that's what we did for this cubic curve, and it's exactly what we could do for any curve. And in fact, that's what we're going to do next. We're going to apply this technique to a specific function that you haven't seen before. Now, for information about horizontal tangents, about increasing and decreasing, and about local maxima and minima, we need the first derivative. But for information about points of inflection, we need the second derivative. Anne.
So let's apply those general techniques to this particular function. It's x to the fourth plus 4x cubed plus 12. We're going to need the first and second derivatives, so let's differentiate it. We get 4x cubed plus 3 fours are 12x squared, and the 12 just differentiates to 0. Now, we need to know when the first derivative is positive, negative, and 0. And the best way of doing that is by a sign diagram. The derivative will factorise into 4x squared into x plus 3. And for the first factor, 4x squared, well, 4x squared is positive everywhere except 0. Now, for x plus 3, x plus 3 is negative to the left of minus 3 and positive to the right. And if we combine these two diagrams for the derivative, we have that a minus times a plus is negative, so it's negative to the left of minus 3. Then between minus 3 and 0, we've got positive times positive, which is positive. And again, to the right of 0, we've got positive times positive, which is positive. So that's all we need to know about the first derivative. Let's move on to the second derivative. So we'll differentiate this expression, and we get, for the second derivative, 3 fours are 12 x squared plus 2 12s, which are 24x. Now, we go through exactly the same process again with the sign diagram, and what it gives us is that for the second derivative, it changes sign at -2 and 0, and to the left of -2, it's positive. It's negative between -2 and 0, and then positive to the right of 0. Let's summarise these results in a table. Here's the table with our 3 important values of x, -3, -2 and 0, and on these 2 lines we've summarised the information on the first and second derivative that we've just found. Now, I've calculated the value of the function at these points. At -3 it's -15, at -2 it's -4, and at 0 it's 12. Now, there's the information about the first derivative. Here at x is -3, we've got a horizontal tangent. To the left of -3, the derivative is negative, which means that it's decreasing. And to the right, the derivative is positive, which means that the function is increasing. So it's negative, 0, positive, and that means that we've got a local minimum. The other place where the derivative is 0 is at x equals 0, and there we have a horizontal tangent. This time, to the left, we've got a positive derivative, which means an increasing function, and also to the right, an increasing function. So, in spite of the fact that we have a horizontal tangent when x equals 0, we don't have a maximum or a minimum. Let's go on now to look at the second derivative. The second derivative changes sign at x equals 2 and x equals 0. So at these 2 points, the tangent crosses over the curve. That means there are points of inflection at -2, 4 and 0, 12. And when we come to sketch the curve, we'll find it useful to know that the first derivative at x equals -2 is 16, which is fairly steep. Now all we need to do is to translate this information into a graph. Bob?
Well, I've got a copy here of the information which Anne has just provided. And the way I like to use tables like this to sketch graphs is, first of all, to put in the horizontal tangents. We had a horizontal tangent at the point -3, -15, -3, -15. There's a horizontal tangent. Then we had another horizontal tangent at the point 0, 12. 0, 12, that's about here. All right, what about the other important points? Well, there was a point of inflection at -2, -4. -2, -4 is about here, and incidentally the slope there was 16, which is quite steep. Then there was another point of inflection at the point 0, 12, but I've already got that taken account of because that happens to coincide with a horizontal tangent. All right, let's have a look at the other information in the table. The function decreases down to the point where x is -3, and there it has a horizontal tangent. And then it increases between -3 and 0, passing through the point of inflection at -2, -4. And then it goes up to this point 0, 12, where it has a horizontal tangent and a point of inflection, and beyond that it continues to increase. Okay, let's try and sketch that. The function decreases down to x equals -3, where there is this horizontal tangent. It increases up to the point -2, -4, where there's a point of inflection, so it crosses over this tangent. And it continues to increase, and it comes up to a horizontal tangent at the point 0, 12. And it crosses over that horizontal tangent because it also happens to be a point of inflection, and then it continues to increase. Well, having drawn the graph, there's perhaps one last point that we should make, that we found out that the function was increasing on the interval from -3 to 0, and again increasing from 0 through to infinity. But in fact, from the graph, it's quite clear that we can stick those two intervals together, and that the function is actually increasing on the whole of the interval from -3 through to infinity.
The technique that we've used here applies equally well to any function that you can differentiate twice. So, we've developed a technique that works for any function that you will meet, and it just involves two very simple things: being able to differentiate the function a couple of times and to solve some inequalities. Once you've done that, you can sketch the curve. To conclude, let's just compare our sketched curve with the computer plot of the quartic. Didn't we do well?